Hey, John here. What do you say before we dive into trees, we talk about one of the techniques we're going to use and apply it to a linked list first. So let's say we have a singly linked list that looks like this. It has 3 nodes in it. Head pointer points to A, B points to B, and B points to C. All right, so we know this and love it oh so well, right? All right, so what if we want to write a piece of code that will traverse this list, as we say, visit all of these nodes one at a time from the head of the list to the tail, right? An in-order traversal, a front-to-back traversal, all right? What does it mean to visit, by the way? Visiting means to perform some function on each node in a general sense. And in this specific example, let's just print out the value, the letter of the node, right? So how would you do this? Well, this is easy enough. You'd say for, we don't even need a, well, you could say for, a node star P equals P head. And then you could say, while what? While, I guess, P head, because you want to wait, oh, not P head. You would say, while star P is not null, right? And then you would say P is P right arrow next. Assuming the usual struct that defines these nodes, which I'll jot down quickly over here. So this would be the node in this example. It would have some fields, char value, and it would have a node star, what did I call it next? Close curly, like that, okay? This loop would point P at whatever P head says. It would say, as long as P is not null, keep on going, right? So what is the body of the loop? As one line in it. C out, double left, what? P right arrow value. And you might put spaces or whatever. Okay, so this would print these out from head to tail. Well, what if you wanted to print them in reverse order? Okay, well, you could either change it over to a doubly linked list and just start at the tail and follow the links going the other way and using prev instead of next, right? But let's say you don't have that option. Let's say we want to traverse this backwards and it is a singly linked list and we have to work with what we've got. Well, let's look at a recursive function that would do this. There's plenty of ways to solve this. Let's look at the recursive way to make this happen. So let's say you have a main down here somewhere, right? And it's going to call what? Like rev. We want to go in backwards order. We're going to pass it p head. Okay, so we've already talked about recursion. Let's apply it here. When you're designing a recursive function, you figure out what's your base case and you kind of work backwards from there. Well, what I'm going to do is I'm going to start at p head. I'm going to rifle through all these nodes until I run into the null pointer over here, and then I'm going to back out, okay? That's all that I'm going to do here, right? I'm going to erase this to make some room. So you get the general gist. Somebody's going to call this rev function. I'm going to make it void. It looks like Vald. Must improve my penmanship, you see. Node star P, right? What is this thing going to look like? Let's take care of our base case. If what? P is null, then return without doing anything, because if P is null, there's nothing to print out, right? Otherwise, what are we going to do? All right, so we're going to come in from P head. We are going to be pointing at A the first time this is called. We don't want to print that out until after we've printed C and B. So what are we going to do? We're going to say rev P next is what we're going to do, which is going to cause this function to re-enter, this time with P pointing at B, and it'll make the same choice. Is P null? No, it points at B. Therefore, what's it going to do? It's going to say rev P next. Now it's going to enter the rev function again. This time P will be pointing at C over here, and it'll ask, is it null? No. Okay, let's go to rev P next. It comes back in here. Now P will be null. Okay, so this is true, and it will return. And when it returns, it'll return back to this rev line when P was pointing at C, right? Because that's the guy who called it when it was null, and then it returned, it came back. And what do we want to do? Well, we're at the end of the list. Well, this is the first one we want to print, so it makes perfect sense that this is where you would see your C out, double left, P right arrow value. And now there's literally nothing to do. It printed out the C, so then return. What happens now? Well, remember, it was called once for A, then A called B, B called C. That's the one we're executing right now. So when this guy returns, he's returning back to the line of code that called rev and passed it the pointer to C, and that was this line of code here again, when P was pointing at B. So when we return from this call, and we execute this line, and now we will have printed out the B. So here's what the output would look like, right? There'd be a C, now there would be the B, because the B guy would print his thing. He then falls off the bottom and returns. Well, where does he return to? Again, he returns back to here, because when rev was called and P pointed at B, it was called when by this line of code here when P was pointing at A, right? So that when it's done with B and it returns, it comes back to this line of code and it will print out A. Okay, and when he's done, he returns, and remember who called the rev function with P pointing at A. It was the main down here that I erased, right? So that's the end of the recursive call. So this definitely printed out CBA in backwards order. This is going to be a theme we're going to see when we talk about how to traverse a tree, okay? All right, so let's do trees now. Let's start with some examples, all right? Let's have a tree that has an A, and a B here maybe, and a C, and have a D over here. D doesn't have any children, so I'm going to go ahead. I'm going to draw the pointers, right? Just to remind us all that there aren't any there. And there aren't any children, but to remember that there are actual pointers involved here, right? And C has what? He's going to have two children's over here. He's going to have an F. He's going to have a G. And let's make this interesting. Let's give F a child over here, H. No pointers for these guys, okay? It's a H. All right. Let's clean that up a little bit. Okay. There's an example binary tree. Okay, it's not strictly binary. It's not almost complete. It's nothing. It's just a run-of-the-mill binary tree, okay? Let's talk about what it means to traverse this thing. In the linked list case that we just talked about, we have front to back and back to front. Okay, this is kind of a different animal here, and there are some standard traversals that we can use for binary trees or trees in general, actually. This case is going to be binary. So let's look at what we do here. So we have what's called a pre-order, an in-order, and a post-order. Order. These are the three standard types of traversals that we'll start with, okay? What happens here is, okay, so the shorthand of it will be this, root, and by this we mean the root of a subtree. We visit, like we were visiting our linked list example, we visit the nodes in this order. We first visit the root of any given subtree, then we visit the left child, and then we visit the right child. It's pre-order. In order, we go to the left child first, then we visit the root, then we go and take care of the right child. Post order, we'll take care of the left child, we'll take care of the right child, and then we'll visit the root. Now you can clearly see pre, in, and post is referring to when the root node itself is visited of a given subtree. So let's look more closely at what this really means. Let's walk through a pre-order traversal of this tree. And we'll write down the letters of the nodes that we encounter in the order that we encounter them, all right? Okay, so what happens in pre-order? I'm going to say go visit the root of a subtree, the left and then the right. So from the top view, what we're going to do is we're going to traverse a tree just like we traverse the linked list. There will be a function that says do a pre-order traversal, and there will be an argument passed into that function that is the pointer to the root of a subtree in this structure. That top level call will simply point at the root of the tree. All right. So what do? We go visit the root, then we visit left and visit right. And just like the linked list, right, for now, the idea of visiting will be to simply print out the value in the node. All right. Again, let's throw up this really quick. Struct node for this example would look like this: character, value. Okay, and then we'd say node star left, node star right. Pardon my upper and lower case, but you know what I mean there. Okay, so what are we going to do? We're going to visit the root first. So when we get called, we're handed a pointer to A right here, and he's going to visit himself. So he's going to print out his key, A. Then what is he going to do? He's going to say, go process my left subtree. So he's going to say, all right, take care of this guy over here. Now, when he takes care of this subtree that's rooted at B, he's going to do the same algorithm here. He's going to process, he's going to visit himself by printing himself out. Then he's going to visit his left child, which is D. And D will be the root of a new subtree that will be processed the same exact way. D is now going to process himself first and visit his left child. There's nothing to do, so that's done. Then he will move on to visit his right child. There's nothing to do, so that's done. So the entire subtree rooted at D is now done. It did these 3 steps, and it completes. It returns. What happens at that point? What it does is it returns back to the logic that was processing B already in progress, right? So B is just finishing its left child, so he then moves on to process its right child, right? So he comes down here and he says, there's nothing down there, so there's nothing to do, and now he's done with his whole task of doing these 3 operations, and he says, okay, I'm done, and he returns to A, which is also work in progress, who has just finished dealing with its left child. This guy now moves on to the right subchild and says, okay, process everything rooted in the subtree at C. C says, fine, I'll execute the rule. Process myself. Print out my value. Now go on to my left child, okay, and process the subtree down here. The rule is process yourself first, F. Process left child, nothing to do, so that's done. Move on to the right child. Now he comes over here to H, says process the subtree in here, and I forgot to put the little null pointers in there, but you know they're there. H says, what do I do first? Visit myself. Print out my value. Visit the left, nothing to do. Visit the right, nothing to do. He's done. He returns to work already in progress at F. F just finished processing its right child, so he's done and returns to the work already in progress at the subtree, I should say, rooted at C, who just finished processing its left child. He then moves on to take care of the subtree rooted at his right child, which is G. The rule for G is visit yourself, take care of your left children, done. Take care of the right child, done. He's done. Returns back to work in progress at C, who just finished its right child, so he's done. Returns to work in progress at A, who just finished his right child, and he's done with the whole thing. This here is the pre-order traversal visitation order of that tree. Let's look at the in-order traversal. Same exact set of rules. Same exact situation. Start at the subtree rooted at the actual root in the tree. Take care of the left child first. Left child starts running. What does he do? Same rule. Process left child first. What does he do? Same thing. Process left child first. Notice no one's visited themselves yet, right? So D is now running. He takes care of his left child. Nothing happens. So now he moves on. What do you do next? Now he processes himself. He visits himself by printing out his value. So he then moves on to his right child. Nothing to do. This is totally done. Returns the work in progress up here at B, who just finished his left child. He visits himself by printing out his key. Visits his right child. Nothing to do. It's done. Goes back to work in progress up at A. A just finished processing its left child. He now visits himself. And he moves on to the right child. Okay, C now runs. What does C do? Same thing. Take care of my left guy first. What does F do? Take care of the left one first. Done. Come back to himself. He needs to visit himself. Move on to the right child. Okay, what does he do? Visit left. Nothing. Visit himself. Done. Visit the right guy. Done. His whole thing is done. Return to work in progress up here at F. F just finished his right child. He's done. Move back to work in progress up here at C, who just finished his left child. He visits himself. Now he moves on to his right child. Okay, what does the right child do? Same thing. Visit the left. Nothing to do. Visit himself. G. Visit the right child. Done. Go back to work in progress at C. He just finished his right child. Done. Go back to work in progress at A. A just finished its right child. Done. The whole thing is done. And this is the order in which these nodes will be visited in an in-order traversal. A post-order. I think you can see where I'm going here with this. We start with a subtree that is the physical tree at A. We visit the left node first. He visits his left first. He visits his left first. Nothing to do. He's done. Fine. Now move on to take care of the right guy. Nothing to do there. Now D visits himself. Okay, post order, he does it himself. You visit yourself last in a post order. So now he returns to work in progress at B, who has just finished his left tree. B then moves on to his right tree. Nothing to do. Comes back, visits himself. Okay, now B is done. Return to work in progress up here at A, who just finished his left child. So A now visits his right child over here, which is C. C visits his left child. F visits his left child. Nothing to do. F now is done with his left child, moves on to his right child, which is H rather. H visits his left child. Nothing to do. H visits his right child. Nothing to do. Visits himself. Prints out his value. F is done with his right child, continues on where he left off by visiting himself. So F now prints out his value. He's done. Return to work in progress at C, who just finished his left child. He moves on to his right child at G. Oops, and he throws the pen all over the place. So C moves on to his right child, which is G. G moves left, nothing to do. Move right, nothing to do. Visit himself. Prints out his value, returns because he's done with the last step over there. C just finished his right child, moves on to visit himself. C is now done, returns to A. A just finished his right child, moves on to the next step, visits himself, and he prints out his key, and again, we're done. So the last one there is the order in which the nodes would be visited in a post-order traversal. All right, so let's look at some code that we could use to implement these traversals. All right. Now, the key of this whole thing, where I'm going, is we're gonna write some recursive routines that work like the singly linked list example when we visited the list in reverse order, namely with recursion. And the reason is recursion is going to take care of remembering the work in progress as we move up and down around as we walk through this tree here. All right. So let's say we want to call some traverse function. I'll just call it T, and we're going to pass it P root. Right. We want to be able to write a traversal function where we just give it a pointer to A, and it will do one of these traversals. Okay. So let's look at how that might work. This would be like what node star P. And what goes in here? Well, it turns out this is the exact same code, but we have to account for two children nodes instead of just a next node that we wrote when running the linked list in backwards, right? So we got to deal with the base case. What is the base case in this situation? Well, it's all these null pointers to the non-existent children, right? So this is going to end up getting called with P set to null all the time. So that is going to be our base case. So we're going to say if there's no P, right? Or you could say P double equals null pointer, then return. Right? If P is null, get out of here. Well, if it's not null, let's look at the pre-order traversal logic. Well, what does it mean to visit a node whose address is handed to you on a silver platter, right? It's P. Well, C out, double left, P value, right? Print out the value. Then what do? Well, you're going to visit the left ones and the right ones, very much like our linked list. So we're going to call T, it's a T, not an F, squiggly T there, TP left. And we don't have to care whether this is null or not, okay? Because obviously, if whatever node we're processing right now has no left child, this value will be null, and that's our base case, so it'll accomplish nothing. When it's done, we move on to our right node, so our right child, I should say, P right. Okay, and when we're done with that, we're done with everything. This is the entire program. Visit yourself, visit your left child, visit your right child. While the left child is running, it's executing a copy of this code, in a different context, right? And when it's done, in the function returns, you just move on to your right one. This is the whole ball game, right? So let's look at the hideous complexity needed to convert this pre-order traversal code to in-order traversal code. Well, what are we going to do there? Well, that's easy enough. Same base case, deal with a non-existent child, and try visiting your left one first before visiting yourself, before visiting your right. And you're done now. Okay, not a problem. Now, I'm going to leave it as a task to the viewer to figure out what we're supposed to do for a post-order traversal. All right, we saw what we changed to go to an in-order, to go to a post-order. I think it's not rocket science to notice that this moves down here. Okay, so this is how you use recursion to perform a pre-order, an in-order, and a post-order traversal on a binary tree, okay? Now, every one of the examples I've given you here, and this definition is I'm going from left to right. The same thing can happen if you decide you want to go from right to left. You just reverse all the R's and L's in here. Instead of going your left child first, you just go to the right one, do that, and then go to your left one. No big deal. It turns out that they're not necessarily mirror images of the traversal order, by the way, but that's okay. The logic still holds. Whether you're going to go left and then right, or right and then left, it doesn't matter. And the choice, by the way, of when to use which one of these traversal orders and whether you're going from left to right or right to left depends entirely on the problem that you're solving. All right, but these techniques represent how to go about implementing a solution to problems of that type. Now, there's one other kind of traversal that we want to talk about here. And the solution is not as simple. Let's call it level order. Now, the way that works is you go by level, right? So remember the depth, right? So up here at depth 0, that's level 0. This is level 1. All these nodes here are on level. These nodes are all on level 2, and this node is on level 3. Okay? Let me erase all this stuff over here. Let's again start by listing these out in level order from left to right. Again, you can do level order from right to left as well as if you wanted to. But let's go from left to right. So what does it mean? It means go left to right of all nodes on level 0. There's only one, that's A. Now go to level 1. And I'm going left to right order, so that would be B and then C. And now go to level 2, left to right. That's D, F, and G. And we move on to level 3. From left to right, it's H. Here are the nodes visited in level order from left to right. If you wanted to visit in level order from right to left, Let's just write that up for the sake of completeness. There's left to right. Here's right to left. Okay, that is just simply visit the first row. From this one would be then C and then B, and then we would go G, F, and D, and then we would go H. Okay, so this left to right, right to left, right? So how do you implement this thing? Well, there's a lot of different ways to do it. One way that turns out as a freebie. I'll leave the more complicated ones as a task to the viewer. Let's look at the, well, I kind of erased it. Let's look at the left to right level order traversal and refer back to the previous video and what it means to store a tree in an array. Now remember, when we stored trees in arrays, they work really well for an almost complete or a complete binary tree. This is neither. But let's look and see what happens if we kind of force this into that array, right? And there's no reason you cannot do this, by the way. This is one way to solve this problem. If you store this tree in an array, remember the rule. What was it? 2k plus 1 and 2k plus 2 to visit the left child and to find the right child for any given node stored at array element number k. Now, by definition, I'm going to erase these numbers here so we don't get confused. By definition, the root node, when you store it in an array like this, is going to be stored at element 0 in this array. So that's going to be where A goes. All right. Now, B and C will be stored using this math. 2k, k is 0, so the left child will be 2 times 0 plus 1. Well, that will be at element 1. That's where B goes. Okay? The right child, over here, C, is going to be stored at 2 times 0 plus 2, which is right there. Now, where does D go? Well, D is a left child of B. B is at 1. Left child is 2 times 1, which is 2, plus 1 is 3, so the D has to go here. All right? What do I do about this? Well, the right child of B should be stored here. 2 times 1 plus 2. All right, so that's 2 plus 2. So that would be at number 4. So in this guy here, I'm going to leave it blank. There's nothing there. We'll just say there's a null there. Okay? I'll put a dot here to remember that I that I mean to leave that blank, all right? That's just to fill this whole thing out. So now we have D is at 3, all right? Where does the left child of D supposed to go, which is also null? So 2 times 3 is 6, plus 1 would be 7. 5, 6, 7. Left child of D is supposed to be null, so I'm going to put a dot in there. The right child of D is going to be the same thing plus 1 more, so that should go here at 8. And there's nothing there for that right child. Okay, that's good. So what then do we do about the left child of C? Who's going to be F? C is at 2. 2 times 2 is 4, plus 1 is, what, 5? Left child of C. 2 times 2 plus 1. Yes, okay. 4 plus 1 is 5. So that's where F goes, right there. Okay. F's, then what? His left child is 2 times 5, which is 10, plus 1 is 11. 9, 10, 11. Oh, you can see this might go on a little bit. And what am I calculating? The left child of F, let's redo that. 2 times 5 plus 1 is 11. So that is a null, right? Because there's nothing there. Now the right child of F is supposed to be here at 2 times 5 plus 2. So that's 12. That's where H goes, okay? What did we not yet do? The right child of C, which is at 2, which should be 2 times 2. That's 4 plus 2 is 6, right? So that's where G goes. And you can see this is all starting to get filled in nicely here. Now 9 and 10 What were these supposed to be used for, right? Well, that is the non-existent children of, like, for example, the node that might have been over here and so on. Because remember, this fits for an almost complete tree. And if we turn this tree we have here into an almost complete tree, that means we have to have a node here and a node here, and we have to have nodes up in here like this, right? In order to make this all fill out, and there would have to be one there as well. So all these nodes here represent all these missing, all these items in here that would be missing. So if we look at this now, the point is, if you put this in here, even though it's sparsely populated, if you ignore these null elements that have nothing in them, what you have here, if you just simply traverse this array now from the beginning to the end, you will visit all these nodes in level order from left to right, right? So that should be A, B, C. We got A, B, C, right? Then we should see D, F, G. There's D, F, and G. And then you should see H. How? So this is one way to do a level order traversal of a binary tree. Now, again, there's many ways to solve these problems. There's recursive solutions and non-recursive solutions to any problem, quite frankly. There are numerous notes in the course website that talk about the variations of other solutions to traversing these trees. So this video can give you the general rundown. When I actually build trees and I have to write a traversal routine myself, I use the recursion that I just drew out for you right here. I never use these other methods, but the other methods can become useful in certain circumstances. There's always reasons to find another way to solve a problem, because you have very specific situations where different kinds of performance improvements are necessary based on the kind of data that you have to process. In order to run quickly, if all your trees that you create are always perfectly balanced, right, or almost complete or complete, you might always just simply store them in an array like this. If it's very sparse or, something else, you probably don't want to do this, because the number of empty nodes could become very large, right? And it becomes memory wasteful at that time. It also depends on what a value is of your node. In this case, the value of these nodes is a single character. So this array, when built, there's a single byte for each one of these things. This is a very efficient way, even if it's only, say, 50% full. You're still pretty good using this array to store this thing. On the other hand, if each one of these nodes has, 1 megabyte of value in it, giant, huge structures with all sorts of things, or that require deep copies and all this other stuff, you may not want to put it in an array like this, because it could just become too cumbersome to have to move them around and even just construct the thing. So hopefully this gives you the insights you're going to need to be able to traverse binary trees. Thanks for watching. See you next time.